This video is about logarithmic functions. Now, the first thing you want to keep in mind is that a logarithm is an exponent. This is something that you really need to keep in the back of your mind. When people hear logarithms, sometimes they get intimidating. It's an intimidating word. But if you ignore the term and just concentrate on its meaning, it's a little easier to swallow. A logarithm is nothing other than just an exponent. It does have a different form in terms of writing it. So we're going to look at two different forms. We're going to look at exponential form and we're going to look at logarithmic form. We're going to see the differences between these two and how they look like. Okay, so in exponential form, we typically deal with a base raised to some exponent equaling some value or some number. So it looks like the name Ben, b to the e power equals n. When it comes to logarithmic forms, we can start by stating what a logarithm is in terms of this. The logarithm is the e, because remember, the logarithm is the exponent. So the exponent here is e. So if I start by writing that, the logarithm is e. We're almost there, we're almost done. Now, in order for something to have an exponent, it also has to have a base raised to that exponent. So the base is b. So we're going to put the base sort of in the basement, way down here. It's almost like a subscript of log. And then the base raised to the exponent has to equal something. So that thing, the n value, the number, is going to go right here. So this is exponential form. This is logarithmic form. It's stating the exact same thing. This is stating that the exponent of b is e. So the log, the exponent with a base of b, is e, and when you take b and raise it to e, you're going to get n as a value out of it. So one of the skills that you're going to want to develop is to be able to convert one form to another form. You should be able to convert. So let's do one for each. Let's convert. Let's say we have 3 to the y equals 7 to logarithmic form. Okay, so this is pretty simple. This is exponential form. Here we have a base to an exponent equaling a number. To convert it to logarithmic form, we start by stating what the logarithm is. The logarithm is y, because the exponent is y and the logarithm is an exponent. So you're just basically saying the exponent is y. Now we want to leave two spaces, the subscript and the value right after the log. The base goes in the basement, so the base is 3, so we have a little base 3, and what it all equals is 7. So this is logarithmic form. Let's go and do it the other way. Let's convert, let's say log base 6 11 equals p to exponential form. Okay, so for this one, The exponential form is a base to an exponent equaling some value. So we start with the base. The base is 6. Then we raise it to the exponent. The exponent is p, because that's what the log equals. And this is going to equal the number 11. So this is the exponential form of that logarithm. 6 to the p equals 11. And I usually call this process sort of taking the trip. The process of starting with the base, raising it to the p, and then it equaling that value right there. And going back to this prior example, if we were to take 3, raise it to the y, and it equals 7, we get our exponential form that we started with. So that's basic conversion problems. You should be able to change from exponential to logarithmic form, and also change from logarithmic form to exponential form. You should be comfortable to do both of those. One thing I did want to mention with the original statement that I had, log base b of n equals the exponent. That's just the basic form of a logarithm. There's a couple things I want to mention here. The n value, n has to be greater than 0. It has to be a positive value. And the reason why is because if you have your base raised to an exponent, you're always going to get positive answers. It's always going to be positive. It's impossible to get the negative. Now, the base also has restrictions. The base also has to be positive, and the base cannot equal 1. So there's two restrictions for the base, or two statements of restrictions. It has to be positive and it can't equal 1. The reason why it can't equal 1 is because if the base is 1, no matter what it's raised to, it's going to equal 1. Same thing for it being 0. And it has to be positive so as to not have an n value be negative. So this n value and b value being greater than 0 sort of have a close connection to one another. Now the exponent can be anything. Okay, so let's move on to something called evaluating logarithms. Now this is also pretty simple if you know basic exponents. For example, if I were to ask you to evaluate log base 2 of 8, what I'm asking you to do is to evaluate the exponent with a base of 2 that ends up giving you 8. In other words, 2 to what power equals 8? That's what this is asking you to do. It's asking you to find out what the exponent of 2 would be that would end up giving you 8. And because 2 to the third equals 8, that's what the evaluation of the problem is. So log base 2 of 8 is 3, because 2 cubed is 8. 2 raised to the third power is 8. Let's do another one. Evaluate log base 3 of 9. This is asking you, 3 is your base. What is 3 as a base? Let me rephrase that. 3 raised to what power will give you 9? 3 raised to what power will give you 9? The answer is 2, because 3 squared is 9. Let's do another one. log base 5 of 1. So this is saying 5 raised to what power? What's the logarithm? So what's the exponent with a base of 5 that will give you 1? 5 to what power is 1? The answer is 0, because 5 to the 0 is 1. Let's do another one. Log base 2 of the square root of 2. So this is saying 2 as a base raised to what power is the square root of 2? Well, if I write the square root of 2 as an exponent instead of as a radical, it's 2 to the 1/2 power. So 2 to what power is 2 to the 1/2 power? It's obviously 1/2. Let's do one more. Say if we had log base 7 of 1 over 49. This is saying 7 to what power is 1 over 49? Well, because the 7 becomes a fraction, then we know that the x value or the exponent needs to be negative, because the negative tells you to flip the 7. So if it was 7 to the negative 1, that would just be flipping 7, which would be 1/7. But if we flip and square, we'll get this. So 7 to the negative 2 would be 1 over 49. So negative 2 is the answer. And another way to look at it is that 49 is 7 squared. And if I move 7 squared up to the numerator, it changes the sign of the value. So for example, let me write it out like this. 1 over 49 is the same as 1 over 7 squared. If I take the 7 squared and I move it up, it becomes 7 to the negative 2. So 7 to what power is 7 to the negative 2? It's negative 2. So that is the second kind of problem that that usually is presented. Usually it's changing one form to another and then evaluating, and then that usually leads to graphing logarithms. So let's take a look at that. Okay, so let's just jump right in and try to, let's just look at a particular function. Let's say if we had y, or f of x equals 2 log base 2 of x minus 1 plus 3. Looks confusing. It looks pretty daunting at first. So what are we going to do with this? Well, the first thing that you should look at and focus in on is this area here. That area represents the log base b of n. The log base b is going to be 2 in that case, and n is going to be x minus 1. This stuff is sort of floater stuff. And you're going to be multiplying by 2, whatever this is, you're going to be multiplying by 2, and then you're going to tack on 3 to it in the end. Why should we focus on this? Well, if we look at this, we're looking at log base 2 of x minus 1. Now when I look at this, I'm sort of focusing on log base 2. I'm focusing on the fact that I've got a base of 2. Now when I'm dealing with log base 2, it would be really nice if I had log base 2 of 1, or log base 2 of 2, or log base 2 of 4, or log base 2 of 8, so on and so forth. The reason why I would say that this would be nice to have is because I know what the evaluation of log base 2 of 1 is. That equals 0. Log base 2 of 2, 2 to what power is 2? That equals 1. 2 to what power is 4? That equals 2. 2 to what power is 8? That equals 3. I know what these are. So if I can recreate that somehow over here, it would make an XY table much easier to churn out. So, how do I do that? How do I create a log base 2 of 1? Well, you ask yourself the question, what value of x minus 1 would give you 1? The answer is 2. So let me show you. If I plug in 2 here, I get 2 minus 1 is 1. Then I'm ending up with 2 log base 2 of 1 plus 3. Well, I know what log base 2 of 1 is. That's 0. So 2 times 0 plus 3. 2 times 0 is 0. 0 plus 3 is 3. So we have a really easy output. We have a point, 2, 3. Okay, let's do it. Let's try to recreate or get a log base 2 of 2. So I'm looking at x minus 1, and I want to have a 2 over there. So if I plug in a 3, I'm going to have 3 minus 1 is 2. So then I'm going to have 2 log base 2 of 2 plus 3. Log base 2 of 2 is 1, because 2 to the 1 is 2. 1 times 2 is 2, and then plus 3 is 5. Okay, so the next one we want to create is a log base 2 of 4. So what value do I need to plug in? Minus 1, that would give me a 4. Well, 5 would do that, because 5 minus 1 is 4. So I would have 2 log base 2 of 4 plus 3. Log base 2 of 4 is 2. 2 times 2 is 4. 4 plus 3 is 7. Let's do one last one. How do I get log base 2 of 8? What value minus 1 is 8? 9. So I would have 2 log base 2 of 9 minus 1, which is 8, plus 3. Log base 2 of 8 is 3. 3 times 2 is 6. 6 plus 3 is 9. Now you might be wondering why I'm putting this value in parentheses, and the reason is because if I don't put them in parentheses, you might add the 3 and the 8 together, and you're not supposed to do that. Okay, so what we have now is 4 points. So let's plot those lines, or those points, and see what this graph looks like. So we want our x values to go up to 9 at least. So 1, 2, 4, 5, 6, 7, 8, 9. And our y values need to go up to 9 also. 1, 2, 4, 5, 6, 7, 8, 9. Okay, so let's plot these points. 2, 3. It's right here. 3, 5. 5, 7, and 9, 9. Okay, so just right now you see that we've got a little bit of a bend here. Now the question is, where is this going to stop? Is it going to just drop straight down? Is it going to cross into this area down here in the third quadrant? What is it going to do? Well, one thing that you can do is you can see here what is happening in terms of the domain. And you can also locate the vertical asymptote from here. So this x minus 1 represents n, the n value. And if you remember back in the video, I said that n has to be greater than 0. So if x minus 1 is n, x minus 1 has to be greater than 0. That means x has to be greater than 1. This is a representation of the function's domain. That means if x has to be greater than 1, there will be a vertical asymptote x equals 1. That's telling you the function needs to be to the right of that value. So what's going to happen is this thing is going to just shoot straight down and get infinitely close to that asymptote. So that is your logarithmic function here. Now, do you always have to set the n value greater than 0 and then solve for x and then interpret that as your domain and your vertical asymptote? Well, not really. If you remember back to when we did, I think it's in the previous video, for exponential functions. If we remember going back to that, where we had y equals a b to the x minus h plus k. That was sort of a very general example or rule of the exponential function. I mean, you could have something like 1/2 3 to the x plus 5 minus 3. The rule was that this exponential function had a horizontal asymptote of y equals k. And in this specific sense, the horizontal asymptote for this was y equals -3. Well, a logarithmic function is going to be a lot like this. But instead of finding a horizontal asymptote, we're going to have a vertical asymptote. So the opposite of that. Now, if you think about it, what would the opposite of y be? Well, it would be x. And if I'm not choosing k, what other value would I choose? You might choose a, but in terms of transformations left, right, up, and down, the difference between up and down, which is the k value, would be left and right. So if we're dealing with h's and k's, I mean, you could deal with other values or other variables depending upon the book. The vertical asymptote would be x equals h. So if you had a problem that said, y equals 3 log base 4 x plus 1 minus 5. That's telling you a lot of information in regards to the transformation, just like the exponential functions. The a value tells you the same as the a value there. This says a vertical compression times 1/2. This says vertical stretch by 3. This tells you the same as this. This says that I'm moving my function down 3 units. This says I'm moving my function down 5 units. The h value here is -5. That's telling you that you're moving left 5 units. My h value here is -1. Remember, you're thinking opposite of what you see. That means I'm moving left 1 unit. So for exponential functions, I would be concentrating on the k value. For logarithmic functions, I'm focusing on the h value, which is the opposite of what you see right by the x. So my vertical asymptote for this function would be x equals -1. So let's go back to this one. My vertical asymptote is going to be x equals my h value. My h value is the opposite of what I see right by the x. I see -1, I think opposite of that, +1. X equals +1 is my vertical asymptote, and you see that right here. There's my vertical asymptote. And that really helps you when you're graphing log functions, because it sort of forces you not to go beyond that x value in terms of domain. So that really helps. So the last thing I want to mention is the relationship between an exponential function and a logarithmic function. They're inverses of one another. Meaning they're symmetric over the y equals x axis. So if you were to graph an exponential function and then on the same graph its logarithmic function, it would be symmetric over the y equals x axis. For example, if you were to just take a regular run-of-the-mill exponential function and then draw y equals x as the axis of symmetry for these, and then you can draw the logarithmic function would look like this. And you can see, so this would be the log function, this would be the exponential function. So you could see that there's symmetry between the exponential function and the logarithmic function. Now, another thing I should mention is that, let's say if you pick a point on this exponential function, like 0, 1, if you take this point and flip it, it becomes 1, 0. You'll see that that point goes on the logarithmic function. That shows that they're inverse functions. In fact, any point, any xy on the exponential function, if you flip those, become points. It'll look like y comma x in comparison to the original point on the logarithmic function. That shows that they're inverse functions.